Alright, welcome back. We have a new problem here. This is from the heat exchanger. 191006 is the heat exchanger problem. First thing we do when we look at problems is we look at the numbers. 1.5 times 10 to the 4, 2.5 times 10 to the 4, 1.1 BT per pound mass degree Fahrenheit, 1.0 BTs per pound mass degree Fahrenheit, 160 degrees, 110 degrees Fahrenheit, 92 degrees. Alright, so looking at those numbers, I don't think anything can mess me up. So now we read the problem. Refer to the drawing of an operating lube oil system, lube oil heat exchanger, see figure below. Alright, lube oil is coming in the shell side, and coming out of the shell side over here. Cooling water's coming in, so it's a cross flow heat exchanger, and cooling water flows on the tube side of this heat exchanger. Alright, so we refer to the drawing. Given the following information, mass flow rate of the oil is equal to 1.5 times 10 to the 4 pound mass per hour. Mass flow rate of the water is 2.5 times 10 to the 4 pounds mass per hour. The specific heat capacity of oil is 1.1 BTU per pound mass. Specific heat capacity of water is 1.0 BTUs per pound mass. Alright, temperature of the oil in is 160 degrees. It's getting cooled off to 110 degrees. So I'm going to go ahead and write that there. Lube oil coming in is at 160 degrees Fahrenheit. And the temperature of the oil coming out is going to be 110 degrees Fahrenheit. I'd recommend you do that as well. Temperature of the circ water in is going to be 92 degrees. We are looking for temperature of the circ water out. So the temperature right here. Okay? So it's pretty normal to see the mass flow rate of the water is a little bit higher than mass flow rate of the oil. Alright. So what are we going to use for this problem? Which of the following is the approximate temperature of the cooling water exiting the heat exchanger? TCW out. So if you look, it's going to be higher than 92, right? Because it's going into hot oil and it's cooling it off. So are any of them less than 92? No. Okay. Excuse me. I know that from my equation sheet, we're going to use this. Q dot equals mass flow rate, C sub P, T hot side minus T cold side. All right. And I also know that Q dot, the heat transfer rate into the oil, or out of the oil, excuse me, is going to be equal to the heat transfer going into the circ water. Cooling water, sorry. So that relationship is going to afford me the ability to do this. Q dot oil equals Q dot circ water. Or mass flow rate, oil, C sub P, oil, times T hot minus T cold, oil. That's going to be equal to, mass flow rate of cooling water, C sub P of the cooling water, and then T hot minus T cold of the cooling water. So, if we do it this way, this is going to be T hot of the oil. This is going to be T cold of the oil. And this is going to be the T cold circ water. And this is going to be T hot circ water. Cooling water, excuse me. And I am looking for the hot temperature of the cooling water. So that's going to make sense here. It's going to keep my my numbers straight, so I won't have a negative number. So what am I looking for? what am I looking for with this equation? Well, I'm looking for this right here. T hot of the cooling water. Okay? So now it's algebra, right? T hot minus T cold cooling water. That's equal to mass flow rate of the oil times specific heat capacity of the oil times T hot minus T cold of the oil. All right. That divided by specific heat capacity of the cooling water and mass flow rate of the cooling water. Now, that is the equation for the delta T, but if I wanted to get the hot side of the cooling water, I would just add T cold of the cooling water. That gets rid of this right here, right? So, now we just plug numbers in. T hot of the cooling water is equal to mass flow rate of the oil, 1.5 times 10 to the 4 pounds mass per hour, 1.5 times 10 to the 4 pounds mass per hour, and times C sub P of the oil, 1.1 BTUs per pound mass degree Fahrenheit, 1.1 BTU per LBM degree Fahrenheit, times difference in temperature in the oil. And I can see from this right here that that's going to be 160 minus 110. The T oil in is going to be 160 minus 110. 160 minus 110. And those are both going to be degrees Fahrenheit. Now that's going to be divided by the C sub P, the specific heat capacity of the cooling water. 1.0 BTU per pound mass degree Fahrenheit. So I'm going to put that right here, 1.0 BTU per pound mass degree Fahrenheit. It's also going to be divided by the mass flow rate of the water, which is 2.5 times 10 to the 4. 2.5 times 10 to the 4 pounds mass per hour. All right, so now change colors here, and I'm going to get rid of my units. It's a very important step. I want you to lay these units out to where you can read them. So pounds mass divided by pounds mass are going to equal 1. Hours divided by hours are going to equal 1. Pounds mass divided by pounds mass are going to equal 1. Degree Fahrenheit divided by degree Fahrenheit are going to equal 1. And BTUs divided by BTUs are going to equal 1. That's going to leave me with degrees Fahrenheit. So, oh look, I forgot to add temperature cold to the circle water, which is going to be 92 degrees. So, plus 92 degrees Fahrenheit. All right, so now I punch these numbers into the calculator. And look, e to the 4 here, divided by e to the 4, that's going to cancel out. Does that make sense? The numbers are just zeros at the end of that 1.5. So, sorry about that. If you want to raise chickens, my wife's Pinterest page is a good place to look. 1.5 times 1.1 times 160 minus 110, it's going to be 50, divided by the quantity, 1.0 times 2.5. That's going to be 33 plus 92 degrees on the cold leg. It's going to be 125 degrees, right? 33 degrees Fahrenheit plus 92 degrees Fahrenheit. That's going to be T hot cooling water. That is going to be 125 degrees Fahrenheit. All right, so what I want you to get out of me working this. One, I want you writing these numbers down. All right, you got hot oil coming in, cold oil coming out. cold water going in, hot water coming out. Does this make sense? Does 125 degrees right here make sense? All right, we don't have a 50 degree delta T. Well, that didn't really matter, but you gained another 33 degrees across your cooling water, and you lost 50 degrees on that. So that kind of makes sense, yeah? What else? We don't have a lower number than 92, and we have a lower number than 160. So I like it. So I'm going to say D is the correct answer. All right. Thank you, and stay tuned for the next one.